Right now, as you're watching this, a pressure system is forming over the Rockies that does not belong in April. It belongs in winter. 986 millibars, and it is not arriving alone. It is the first pulse of a 12-day atmospheric pattern that has already locked itself into place over North America, a conveyor belt of Pacific energy crossing the Rockies every 48 hours and detonating across the Central Plains. Tornadoes, blizzard, wildfires, flooding, 60-mile-per-hour winds, all from one storm, then a second storm, then potentially a third. The models agree on the pattern. They are genuinely divided on the outcome. Will it concentrate into one catastrophic event that history never forgets, or disperse into 100 storms that history barely notices? Stick around. That answer is coming. If this has you hooked, hit like and subscribe to the Skylab, because this story is not finished, and you will want to be here when the atmosphere finally shows its hand. Drop a comment below. I want to know where in the world you are right now, whether you are inside the risk zone or watching this from somewhere completely different, and your honest answer to this. If one single cyclone can simultaneously produce tornadoes, a blizzard, wildfires and flooding across a continent in late April, is this just a powerful spring storm, or is the atmosphere trying to tell us something about what the rest of this season looks like? Tell me what you think. Now let us get into it. Part 1. The 986 millibar problem. There is a number sitting in the forecast models right now that should not be there. 986 millibars. That is the projected central pressure of the cyclone forecast to slam into the northern plains on April 23rd. Write that number down, because by the time this video is over, you're going to understand exactly why that number is the difference between a forgettable spring storm and something that rewrites this entire country's weather story for the next 2 weeks. 986 millibars does not belong in late April. It belongs in January. It belongs in the kind of winter systems that shut down cities, collapse roofs, and make meteorologists reach for words they normally reserve for December. And yet, here it is, sitting in the forecast guidance for a Thursday in spring, as calm and indifferent as if it had always planned to be there. To put it in perspective, the climatological average central pressure for a late April cyclone over the central United States is somewhere around 1000 to 1004 millibars. That is just the normal background behaviour of the atmosphere during this time of year. Systems form, they move, they produce some rain, maybe some gusty winds, and then they exit. That is the spring weather script that plays out across most years without incident. What we are looking at right now is not that script. A 986 millibar reading places this system in roughly the bottom 5 to 10% of all pressure readings for this time of year. That means that out of every 100 late April cyclones in the historical record, approximately 90 to 95 of them were weaker than what is about to happen. You're not watching average. You're watching an outlier dressed in spring clothes. The seasonal mismatch is the first thing that should catch your attention, because pressure depth alone does not tell the whole story. What makes a winter storm dangerous is the combination of its low pressure and the cold air it drags with it. But late April adds something that winter does not have in the same abundance, which is atmospheric instability. The boundary layer is warming. Gulf moisture is pulsing northward. The sun is now high enough in the sky to heat the surface aggressively. So when you take a system that has the mechanical structure of a January cyclone and you drop it into an environment that has April's thermodynamic energy, you are not just adding two things together, you are multiplying them. The atmosphere does not behave linearly when you cross those kinds of boundaries, and that is part of why the forecasting community is watching this particular system with an unusual mixture of confidence and alarm. Because here is where the story starts to widen into something genuinely difficult to comprehend. This single cyclone, this one system, is not going to produce one type of hazard. It is going to produce 5 of them simultaneously, spread across a geographic footprint that covers the better part of a continent. While meteorologists are watching the tornado threat unfold across the Central Plains, fire weather watches are being posted across the southern high plains, where critically low humidity and powerful downslope winds will push fire spread to dangerous levels. While that is happening, the northern edge of the same system is wrapping cold air into the Dakotas and Montana, where blizzard conditions are forecast with heavy snow and near zero visibility. Meanwhile, the upper Midwest is staring down the barrel of a flooding scenario fueled by saturated soils, snowmelt, and a fresh round of heavy rainfall all arriving at roughly the same time. and stretched across 7 states between all of those other hazards, a wind field capable of sustaining 60 miles per hour gusts is going to make its presence known whether or not a single tornado touches down. 1 storm, 5 hazards, 1,000 miles of active danger. But if anyone's signal in this setup demands your attention above all others, it is the significant tornado parameter, and right now that value is forecast to reach 10. Let that number register for a moment. The significant tornado parameter, which meteorologists call STP, is a composite index that combines several atmospheric ingredients known to support violent tornado production. We are talking about convective available potential energy, which is the fuel load for storm intensity. We are talking about wind shear, which is the change in wind speed and direction with height that gives supercell thunderstorms their rotation. We're talking about storm relative helicity, which measures the corkscrew spin available in the lowest levels of the atmosphere. And we're talking about lifted condensation level height, which tells you how close to the ground a storm's cloud base forms, a critical factor in tornado intensity. When you combine all of those parameters into a single number, you get STP, and that number is normally well below 1. Values above 3 begin to correlate with environments capable of significant tornadoes. Values above 5 are associated with historically dangerous setups. The record books do not have many comfortable entries for STP values above 8. And Thursday's forecast is showing 10. That is not a typo. That is not model noise. That is a signal that the scientific community takes very, very seriously, and the reason it is being watched with such intense scrutiny is that STP does not tell you a tornado will happen. It tells you the atmosphere is capable of producing one of the most violent tornado environments in the observational record if everything else aligns. The word if is carrying enormous weight in this story, and we are going to spend a lot of time with it. Here is the thing about this 12-day period that makes this story larger than any single system. The forecasters tracking this pattern are not looking at one storm. They have identified 3 distinct severe weather windows already taking shape in the model guidance, separated by days but connected by an underlying atmospheric structure that is going to keep generating these events like a factory that cannot be switched off. April 23rd through the 24th is window 1, April 25th through the 28th is window 2, and somewhere out near May 3rd through the 6th, a third window is materializing, lower confidence, higher uncertainty, but present in enough model runs that it cannot be dismissed. So the question this video is really asking is not what will happen on Thursday. The question is why, despite having an environment that screams catastrophe, the outcome remains genuinely undecided. The forecasters have enormous confidence that this cyclone is going to form. They have significant confidence that severe weather will occur across a large area. What they cannot tell you with confidence is whether Thursday produces one tornado that people will still be talking about in 20 years, or whether the energy disperses across 100 storms that collectively cause damage but individually leave no single defining mark on the historical record. The environment is extreme, the trigger is uncertain, and that gap, that space between what the atmosphere is capable of and what it actually delivers, is where this entire story lives. The pattern that is unfolding across the next 12 days may well define the 2026 severe weather season. It is not a blip. It is not an isolated event. It is the opening pulse of a locked atmospheric regime, and the reason it is locked, the reason it is not just going to move on after Thursday, is a story that gets stranger and more fascinating the further you go. But to understand where this is going, you first have to understand what this storm actually is, because a 986 millibar cyclone in late April does not just show up. Something built it. Part 2. A storm. Built like January, occurring in April. Something unusual is happening in the pressure gradient right now, and the pressure gradient is where you find the first clue about why this storm is behaving like it does not belong in the calendar. When meteorologists look at a surface pressure map, they are reading a story written in isobars, which are the lines connecting areas of equal pressure. The closer those lines are packed together, the more dramatic the pressure change across a short distance, and that pressure difference is what drives wind. During most late April systems, the isobars are relatively relaxed. The gradient is gentle. You get maybe 20 or 30 mile/hour winds in the stronger gusts, and the system moves through without generating anything resembling a sustained wind threat. What is being projected for this cyclone is a pressure gradient tight enough to drive sustained winds of 30 to 50 miles per hour across a massive area, with gusts well above that. The isobar spacing on the model maps for this event looks like something you would expect in February. The atmosphere is not reading the calendar. Now compare that pressure structure to a typical winter cyclone. You would find a similar central pressure, you would find a similar radial wind field, you would find a similar storm structure in terms of the geography of airflow around the system. The winter equivalent of this storm would cause major disruption across whichever region it crossed, but it would also be expected because winter is when systems like this are climatologically normal. The truly anomalous part of Thursday's setup is not just that the pressure is low, it is that everything feeding that pressure is operating simultaneously at maximum efficiency in a season that usually prevents that. The upper-level jet stream is the engine, and right now the jet stream is doing something that it reserves for its most dramatic performances, which is producing a jet streak of roughly 130 knots over the central United States. A jet streak is not just a fast part of the jet stream, it is a specific dynamical feature that creates regions of divergence, which means the upper atmosphere is literally spreading apart and lifting air away from the surface in certain locations. When you have strong upper-level divergence over a surface cyclone, you're essentially creating a vacuum. The surface low deepens because air is being evacuated from above faster than it can fill in from the sides. This is the mechanism behind rapid intensification, and for this cyclone it is working at full capacity. The trough, which is the southward dip in the jet stream pattern that precedes most cyclone formation, is also doing something specific that accelerates this process. It is undergoing what meteorologists call negative tilt. As a trough moves eastward, it can rotate from a relatively neutral orientation into one where the southern end is lagging behind the northern end, creating a backwards-leaning configuration. This negative tilt configuration dramatically enhances the lifting dynamics on the eastern side of the trough, which is exactly where this cyclone is going to be sitting on Thursday. Negative tilt is not rare, but negative tilt combined with a 130-knot jet streak and a surface low that has already deepened to 986 millibars is a constellation of factors that does not assemble itself in late April without something significant following. The formation mechanism is what is known as Lee cyclogenesis, and the Rocky Mountains are the essential ingredient. When air flows over a mountain range and descends on the other side, the descending air undergoes stretching in the vertical dimension, and the physics of rotating fluid dynamics means that this stretching generates cyclonic spin at the surface. The Rockies are essentially a storm factory built into the geography of North America, and every time a strong Pacific shortwave crosses them, the potential for a new surface low emerging on the eastern slopes exists. What makes Thursday different from most Lee cyclogenesis events is that the shortwave crossing the Rockies is already carrying more energy than most spring systems, and it is arriving into an environment that is primed to amplify it in three separate and compounding ways. The first compounding factor is the jet dynamics we already discussed. The second is the orographic effect itself, which is adding the initial spin and deepening the system through the Lee cyclogenesis mechanism. The third factor is latent heat release. Once thunderstorms begin firing along the warm sector of this cyclone, they release enormous amounts of heat into the mid-levels of the atmosphere. That heat further lowers the surface pressure by reducing the weight of the air column above the low. So as storms develop Thursday afternoon and evening, they will be actively deepening the system that is producing them. It is a feedback loop that is already baked into the forecast, and it is part of why the confidence in the cyclone's final intensity is actually quite high, even while the tornado outcome remains unresolved. Late April is normally a different story precisely because the thermodynamic energy is not usually matched by this kind of dynamic support. In a typical late April setup, you might have tremendous instability because the sun is doing its job and the Gulf of Mexico is pumping warm, moist air northward, but the jet stream dynamics are usually weakening as winter recedes. You get the fuel without the ignition in the upper atmosphere. Or alternatively, you get a strong upper-level system, but the boundary layer has not heated enough to produce the instability you need for violent storms. The two ingredients do not usually coexist at their respective maximums this late in the season. What is happening this week is that they both are. The warm sector of this cyclone is feeding from Gulf of Mexico moisture that is streaming northward in a corridor of southerly flow ahead of the system. surface dew points across Oklahoma and Kansas are forecast to reach the low to mid-60s Fahrenheit by Thursday afternoon, which is the kind of moisture loading that supports explosive instability. When you take that moisture content and apply surface heating from a late April sun angle, the convective available potential energy values that develop are enormous. The atmosphere is building enormous reserves of energy in the lowest kilometre of the atmosphere, and the question of where and when that energy gets released is the question that the central thread of this entire story returns to again and again. This is the key insight that a simple, strong storm framing misses. This system does not just have deep pressure, it does not just have strong dynamics, it does not just have good moisture, it has all of those things at once, in the kind of mutual amplification that crosses the threshold from significant to potentially historic. The cold core dynamics of the upper level system, which drive the jet and the trough mechanics and the pressure gradient, are being paired with a warm sector that has full spring-level instability. Meteorologists sometimes call this dual-mode amplification because the system is simultaneously being forced from the top down by the jet and from the bottom up by instability release. Each process reinforces the other, and the result is a system whose mechanical structure looks like January, but whose thermodynamic content looks like May. There is a question worth raising here, carefully and with appropriate uncertainty. Are we seeing more of these hybrid systems than we used to? Events where the seasonal boundaries seem to blur, where winter-level dynamics appear in spring environments, or where spring instability arrives earlier than climatology would suggest? The honest answer is that the attribution science is genuinely complex, and this video is not the place to resolve that question. But the pattern deserves acknowledgement, and the observation that something that looks like January is occurring in April is not a small footnote. It is the fundamental anomaly that makes this event what it is. The structure is now set, the dynamics are in place, the moisture is arriving, the jet is aligned, the trough is negatively tilted, the Lee cyclogenesis is underway. Everything that needed to be built has been built, but knowing the engine is powerful is not the same as knowing where the car goes. The geography of initiation, the specific zones where this system concentrates its most extreme energy, tells a very different and much more uncertain story. And that story begins at a location that meteorologists have a very specific name for, a location where 3 atmospheric boundaries converge into a single zone of maximum potential, a location that is, at this moment, centered directly over Kansas and northern Texas. Part 3. The Triple Point Trap. Every major severe weather setup has a geography, and this one has a very specific address. Somewhere along a line running through central Kansas and bending down into northern Texas, 3 separate atmospheric boundaries are about to converge into a single zone of maximum atmospheric tension. Understanding why this matters requires briefly understanding what each of those boundaries is. The warm front is the leading edge of the warm, moist Gulf air that is streaming northward. It is a sloping surface along which air is being lifted and clouds are forming, and it stretches roughly east to west across the northern tier of the warm sector. The cold front is the advancing western edge of the cold air that the cyclone is dragging equatorward, a sharp boundary across which temperature, humidity and wind all change dramatically over very short distances, and the dry line is a feature unique in its prevalence to the central United States, a north-south oriented boundary that separates the humid Gulf air to its east from the hot, dry continental air coming off the elevated terrain to its west. Where all 3 of these boundaries meet is called the Triple Point. It is not a metaphor, it is a literal geographic location where the warm front, cold front and dry line intersect, and it is the most dynamically favoured location for storm initiation in the entire country. The reasons are almost elegant. At the Triple Point you have the moisture convergence from the dry line bringing unstable Gulf air into the zone. You have the lift from both the warm front and the approaching cold front to help release that instability. You have maximum wind shear because the transition between all 3 air masses compresses the change in wind velocity across an extremely short distance. And you have mesoscale boundaries, the small-scale atmospheric features that can act as local focusing mechanisms for convective initiation, clustering in precisely this region. The Kansas to northern Texas corridor is where that triple point is projected to sit on Thursday afternoon and evening, and it maps almost perfectly onto the region showing STP values near or above 10. This is not coincidental. The triple point is a STP maximizer, because it concentrates every ingredient that index measures into a single geographic zone. High CAPE from the Gulf moisture, high shear from the boundary convergence, high helicity from the rapid wind rotation in the lowest layers of the atmosphere, low lifted condensation level height from the high surface dew points. Everything that has to be high is high, and everything that has to be low is low, all in the same place at the same time. But the triple point setup does something else that is less intuitive and arguably more important. Triple point environments tend to produce fewer storms with higher individual intensity. This is the opposite of what a casual observer might expect. When you think about more atmospheric energy, you might naturally think about more storms. But in convective meteorology, concentration matters more than raw quantity. Isolated supercells, those rotating thunderstorm structures that represent the pinnacle of tornado-producing storms, need room to breathe. They need to be able to process the environmental wind shear and moisture without interference from neighbouring storms. When storms fire too closely together, they compete for the available instability. They generate outflow boundaries that disrupt each other's inflow, and they often merge into linear systems that are much more efficient at producing straight-line winds and large hail than tornadoes. The triple point environment, by limiting the number of initiation points, tends to keep storms isolated longer, and isolated storms in environments with STP values above 8 are the setups where history gets written. There is also a secondary low that deserves attention. The primary surface cyclone will be located somewhere in the central to northern plains, but a secondary low is developing along the dry line near the Oklahoma and southern Kansas border. Secondary lows are common in major cyclone events, but their presence here is significant because they act as local convergence enhancers. The secondary low creates additional atmospheric lift in its immediate environment, providing another focusing mechanism for storm initiation that is separate from the primary cyclone. Where the secondary low sets up precisely will be one of the key model-to-model disagreements heading into Thursday, and small errors in its position could shift the highest risk zone by 50 to 100 miles. The timing of this entire setup is also deeply connected to something called the late-day alignment. The atmosphere goes through a daily cycle in terms of its energy content, and late afternoon represents the peak of that cycle, because the sun has been heating the surface for hours, and the boundary layer has accumulated its maximum instability. At the same time, the jet stream dynamics, which operate on a much longer timescale, are continuing to evolve and strengthen through the day. On Thursday, the models are projecting peak instability and peak shear to align somewhere in the 9 to 10 p.m. Central Time window, which creates two significant complications. The first is that nighttime tornadoes are substantially more dangerous than daytime tornadoes because people cannot see them. The warning times are still usually adequate with modern radar, but the fatality statistics for nighttime events are consistently higher even for comparable storm intensity. The second complication is that the verification of storm initiation and storm mode will be happening in the dark, which limits visual confirmation from storm observers and adds an additional layer of uncertainty to the real-time forecasting. Here is where the central question of this story reappears with full force. The triple point environment is maximally favourable. The ingredients are assembled, the geography is focused, but will the storms fire in the right place, at the right time, in the right mode? Model guidance is not fully agreeing on initiation timing, and a disagreement of even 2 to 3 hours in a setup that peaks this late in the evening can be the difference between discrete supercells in darkness and a linear system that has already swept through. There is no forecast tool in existence that can resolve that disagreement with confidence at 1 to 2 days range. The human forecasters at the Storm Prediction Center know this, and the language in their outlooks reflects it. Carefully phrased, heavily conditional, loaded with probability estimates that acknowledge the extremes on both ends. The triple point is a trap. In the best and worst sense of the word, it traps atmospheric energy, concentrates it, focuses it, and prepares it for release. But the mechanism of release, the specific chain of events that determines whether one supercell or 20 storms fires first, remains outside the grip of deterministic forecasting, and the value of understanding that uncertainty is not to dismiss the threat. It is to understand that the real danger in this setup is not reduced by the forecast uncertainty. It is, in a specific and troubling way, amplified by it. The STP value of 10 is the number that next section will examine in full, because that number has a history, and that history is worth knowing before Thursday arrives. Part 4, STP equals 10, the outlier signal. There is a specific category of atmospheric measurement that forecasters treat differently from all the others, and STP values above 8 belong to that category. To be precise about what a significant tornado parameter value of 10 represents, it is helpful to understand where that number sits in the distribution of all STP values ever computed over the United States. The vast majority of days in any year have STP values near 0 across most of the country. Values above 1 begin to correlate with environments capable of significant tornadoes, defined as EF2 or stronger. Values above 3 move into territory associated with historical outbreaks. Values above 5 enter the range associated with the most dangerous tornado environments in the modern observational record. Values above 8 are, statistically, approximately the top 1% of all STP environments ever observed. They are not theoretical maximums, they occur. But they do not occur often, and when they do, the tornado record tends to remember what happened. The environment of April 27, 2011, which was the core day of the April 26th through 28th outbreak, the deadliest tornado outbreak in modern United States history, featured STP values that reached into this range across Alabama and Mississippi. The 2013 Moore, Oklahoma tornado environment, which produced an EF5 wedge tornado with a mile-wide damage path, sat within this general tier of environmental parameters. These are not offered as predictions of what Thursday will produce. They are offered as context for understanding what the forecasting community means when they look at STP-10 and treat it with extreme seriousness. These kinds of environments have antecedents, and the antecedents are not small. But here is the nuance that separates careful science communication from fear-mongering, and it is essential to understand. STP is an environmental index. It measures the capability of the atmosphere to support violent tornado production if supercell thunderstorms develop and maintain discrete structure. It is not a forecast of storms. It is not a forecast of tornadoes. It is a measurement of the room the atmosphere has created for violent outcomes if the convective process behaves in a specific way. The loaded weapon analogy is not imprecise. A weapon with ammunition, a charged spring, and a clear barrel is dangerous. It is genuinely, objectively dangerous. But it does not fire unless someone pulls a trigger, and the atmospheric equivalent of that trigger, storm initiation along the dry line in the correct mode and spacing, is the variable that STP does not and cannot measure. There are two fundamental failure scenarios for this setup that reduce the tornado outcome despite the extreme STP values. The first is cap failure in the wrong direction, meaning the convective inhibition layer, which is a temperature inversion that acts as a lid on storm development, remains strong enough through the evening to prevent any storms from firing at all. This sounds like a beneficial outcome, and for tornado risk it is, but the same cap that suppresses storms all evening can break catastrophically in the overnight hours, releasing all of the accumulated instability at once in a region where public preparedness has already begun to relax. The second failure scenario is storm clustering. If storms fire early along the cold front or along an outflow boundary from elevated convection to the north, those storms can produce a pool of cold air at the surface, called a cold pool, that undercuts the favourable environment ahead of the dry line. When that happens, storms shift from discrete supercells into a squall line or bow echo structure, and the tornado efficiency of the system drops dramatically even as the wind damage potential remains high. These are not obscure edge cases. They are the two most common reasons why extreme STP environments fail to produce the tornado outcomes that the raw numbers suggest. The success scenario is simpler to describe and harder to achieve. One or two isolated supercells fire along the dry line in the triple point zone during the peak shear window. They maintain discrete structure long enough to establish strong mesocyclone rotation, and they remain on the ground long enough for the atmospheric flow to carry them northeast along the boundary. Long-track tornadoes, the kind that travel dozens of miles across the ground, typically require continuous mesocyclone structure, sustained over a minimum of 30 to 45 minutes. This requires the supercell to not be disrupted by neighbouring storms, by outflow boundaries from other convection, or by a transition in storm mode. When all of those conditions are met simultaneously, and they are not met in most setups, the result can be a tornado that moves through multiple counties and produces damage that the EF scale assigns to its highest categories. The timing issue for peak STP values adds another dimension to this risk. The models are projecting maximum values in the 9 to 10 pm Central Time window, which means that if discrete supercells do fire during the peak shear period, they will be doing so after dark. Nighttime supercells are not inherently stronger than daytime supercells. In some respects, they are weaker, because they lose the surface heating that drives inflow, but from a life safety perspective, they are dramatically more dangerous for a reason that has nothing to do with storm physics. People are home, people are asleep. The visual cues that allow a person watching daylight skies to recognize a wall cloud or a developing tornado funnel do not exist at 10 p.m. in May. Warning dissemination is effective but not perfect, and the demographics most at risk, elderly individuals, people in manufactured housing, communities with limited English access to warnings, have statistically higher fatality rates during nighttime events. The dryline mixing variability adds one more layer to this already complicated picture. During the afternoon hours, solar heating causes the boundary layer to mix vigorously, and this mixing can either sharpen the dryline, concentrating the moisture contrast and making it more effective as a boundary for storm initiation, or it can diffuse the dryline, smearing the moisture gradient across a broader zone and reducing the focusing effect. Model guidance shows disagreement on exactly how aggressively the dryline will mix on Thursday afternoon, and that disagreement matters because a sharp, well-defined dryline is a much more reliable initiation boundary than a diffuse moisture gradient. The uncertainty in dryline structure is one of the reasons that even experienced meteorologists examining the same model data are producing a range of probability estimates for discrete supercell development. So we are left with a number, 10, that represents one of the most dangerous atmospheric environments in the historical record, in a setup that cannot guarantee the trigger that converts that environment into its worst possible outcome. That tension between extraordinary potential and genuine uncertainty is not a flaw in the science. It is the science. It is the honest, unvarnished truth about how the atmosphere works, and it is why this story is not simply about the numbers, but about what the numbers mean and what they do not. What those numbers do mean at the scale of the entire country is something the next section will show you, because the tornado threat is only one of 5 simultaneous hazards, and the other 4 are not waiting for the atmosphere to make up its mind. Part 5. The 5-hazard snapshot, continental scale. Draw a mental map of the United States, and then imagine drawing a circle that stretches from the Texas Panhandle to southern Canada, from the foot of the Rockies to the Mississippi River. That circle roughly contains the hazard footprint of this single system on a single day. Within that circle, on Thursday, 5 separate and largely independent hazard processes will be operating simultaneously, each driven by a different component of the same cyclone, each representing a genuine threat to life and property in its own right. The tornado story is the one that captures headlines, and it should, but the breadth of simultaneous danger across this footprint tells you something important about the scale of what is unfolding. This is not a storm that threatens one region, it is a continental scale engine whose different components happen to produce different flavors of disaster, depending on where you are standing. Start in the southern high plains, specifically across the Texas and Oklahoma panhandles and southeastern Colorado. While the dryline drama plays out to the east, the western side of the dryline is experiencing an entirely different atmospheric story. The dry, descending air flowing down from the elevated terrain is combining with very low relative humidity, which in late April can drop below 15% during the afternoon, and winds that will be sustained at 40 to 50 miles per hour. Fire weather watches and red flag warnings are not issued casually. They require a specific combination of low humidity, low fuel moisture, and strong winds that together create conditions under which a spark, any spark, becomes a potential catastrophe. The vegetation across this region has dried rapidly through the spring season, and a fire starting under these conditions can travel faster than a person can run. The fire weather threat in this setup is not secondary to the tornado threat. It is a parallel catastrophe track operating in a different geography. Shift your mental map northward to the Dakotas and into Montana. Here, the cold sector of the cyclone, the region behind the warm front where polar air is descending, is going to do something that would not surprise a meteorologist, but would deeply confuse a casual observer. It is going to produce a blizzard, not a moderate snow event. A blizzard with the specific combination of heavy snow rates, reduced visibility to near zero, and sustained winds that create whiteout conditions across open terrain. The mechanism is the classic cold sector wraparound. As the cyclone's counterclockwise circulation pulls cold air southward on its western flank, it simultaneously wraps moisture-laden air from the warm sector around and into the cold zone, feeding precipitation into a region that has the temperature profile to produce snow. The deformation zone, which is a region of horizontal stretching and narrowing in the wind field that concentrates precipitation in a narrow band, will place the highest snow totals in a corridor where rates of 3 to 4 inches per hour are possible. April blizzards are not unheard of in the northern plains, but April blizzards occurring simultaneously with EF-scale tornado potential, 3 states to the south, are a meteorological fingerprint of an unusually powerful system. Move the mental map eastward into the upper Midwest, across Wisconsin, Minnesota, Iowa, and parts of Illinois. This region has been receiving above normal precipitation for weeks. The soil moisture is already saturated in many areas, meaning that additional rainfall cannot be absorbed into the ground, and instead runs immediately into streams and rivers. The snowpack across parts of Minnesota and Wisconsin is still melting, adding additional water to a drainage system that is already at or above capacity in many locations. The forecast rainfall totals ahead of this system range from 1 to 3 inches across the corridor, and in a normal spring this would be absorbed without consequence. In the current hydrological state, it is going straight into rivers that are already running high. Flood watches and warnings in this region are not responding to the storm's rainfall alone. They are responding to the system's rainfall arriving on top of everything that has already accumulated, and the combined load exceeds the capacity of the drainage infrastructure across multiple river basins. And then there is the wind. Not the wind associated with tornadoes, not the wind generated by storm outflow, but the sustained large-scale wind field driven directly by the pressure gradient of the cyclone. A 986 millibar cyclone produces a wind field that extends hundreds of miles from its center and across a 7-state area that arc from Wyoming to Wisconsin. Sustained winds of 30 to 45 miles per hour with gusts to 60 miles per hour are forecast independent of any storm activity. This means that even in areas where no severe weather develops, the wind alone will be knocking down trees, damaging structures, creating dangerous driving conditions for high-profile vehicles, and disrupting the power grid for hundreds of thousands of customers. The reason the United States is uniquely susceptible to simultaneous continental-scale hazard events like this comes down to geography. North America is oriented in a way that makes atmospheric collisions between air masses almost inevitable during spring. The Rocky Mountains form a north-south barrier that forces Pacific air to behave differently on each side, but there is no equivalent east-west barrier to stop the interactions that happen downstream. Cold polar air from Canada can push all the way to the Gulf of Mexico without encountering any significant terrain. Warm Gulf moisture can stream northward into the plains without obstruction. When these air masses meet along a frontal zone that is being dynamically forced by an upper-level trough, the result is not a localized event. It is a multi-region event because the battlefield between those air masses extends across 1,000 miles of relatively flat terrain. Compare this briefly to Eurasia, where the Himalayas and the Tibetan Plateau act as a genuine barrier between tropical and polar air masses during certain seasons, and the result is a very different kind of severe weather climatology. The central United States is uniquely configured to produce events like Thursdays, and that unique configuration is both a source of the country's meteorological fascination and a recurrent driver of its weather-related losses. The concept of compound hazard days, those events where multiple distinct extreme weather processes occur simultaneously across the same general region, has been a growing focus of research because the interplay between them creates risks that are larger than the sum of their parts. Emergency management systems are built to respond to one major event. They are not optimized for 5. Evacuation routes that might work for a flood zone can be compromised by wind-driven debris. Fire crews responding to Southern Plains fires cannot be redirected to assist in blizzard rescue operations in the Dakotas. The logistics of simultaneous multi-hazard events stress response capacity in ways that single-event planning does not anticipate. This is day 1 of 12. If a system this complex, this spatially extensive, and this energetically loaded is only the opening act of a locked atmospheric regime that will keep generating similar events every 48 to 72 hours, what does the accumulation of those events look like by day 12? The answer to that question requires understanding why the atmosphere does not simply move on after Thursday, and that means going one level higher in the atmospheric hierarchy, above the surface cyclone, above the jet stream, into the large-scale wave structure that is keeping this entire pattern locked in place. Part 6. The conveyor belt. Imagine a factory that assembles weather systems. The raw material arrives from the Pacific Ocean as atmospheric energy organised into disturbances called short waves, which are compact areas of enhanced spin and lifting embedded within the broader jet stream flow. These short waves travel eastward with the jet, and when they encounter the Rocky Mountains, they trigger the Lee cyclogenesis process we discussed earlier, generating new surface lows on the eastern slopes. Under normal atmospheric configurations, a short wave crosses the Rockies, generates a cyclone. The cyclone moves northeast across the Central Plains, exits into Canada or the Great Lakes, and the whole pattern resets. This takes about 3 to 5 days, and then there is usually a period of quieter weather before the next shortwave arrives. What is happening right now is not the normal configuration. The Pacific shortwave train, which is the term for a series of successive disturbances arriving at roughly regular intervals from across the Pacific Ocean, is delivering shortwaves to the western United States at a frequency of approximately 48 to 72 hours. That means before the cyclone generated by shortwave 1 has even cleared the region, shortwave 2 is already crossing the Rockies and beginning to generate its own surface low. And before shortwave 2's storm has completed its life cycle, shortwave 3 is in the door. The factory is not on a normal production schedule, it is running triple shifts. The term pattern lock describes exactly what this sounds like. The large-scale atmospheric configuration over North America is not evolving through its normal progression of weather regimes. It is stuck, or more precisely, it is being held in a state by large-scale wave dynamics that favour the persistent establishment of a deep trough over the western United States and a ridge over the eastern part of the country. This configuration places the zone of maximum atmospheric conflict, the boundary between cold polar air to the west and warm Gulf air to the east, directly over the Central Plains, and it keeps it there, day after day, system after system. The model guidance is showing remarkable consistency in this pattern for the coming 12 days, which itself is noteworthy because extended model forecasts are usually degraded by uncertainty beyond about a week. When models that normally diverge significantly at 10 to 12 days are showing the same fundamental configuration, it is a signal that the underlying large-scale pattern is robust enough to overcome the normal sources of forecast error. Meteorologists call this a high signal-to-noise ratio, and it means that the confidence in the existence of multiple severe weather windows is higher than normal, even though the confidence in any individual storm's details remains limited. What is also important to understand is that these are not truly separate storms in the way that a casual weather map reading might suggest. Each system inherits the environmental preconditions left by the previous one. Soil moisture from the flooding episode associated with the first system increases evaporation and available moisture for the next system. The anomalous Gulf moisture transport is continuous because the large-scale wind pattern is continuously directed to funnel Gulf air northward. The atmospheric instability that gets tapped by one system does not fully recover before the next system arrives to tap it again. There is a sense carefully framed in which these individual storms are successive releases of the same large-scale energy reservoir, rather than independent events that happen to occur in sequence. This raises a subtler and somewhat counterintuitive possibility. If each storm partially uses but does not fully deplete the available instability and moisture, and if the pattern lock is maintaining a continuous supply of both, then later storms in the sequence might actually operate in an environment that has been preconditioned to be more efficient. The moisture that evaporated from flooded soils and vegetation after the first system adds to the total moisture loading for the second. The destabilized atmosphere recovers between events, but perhaps not fully. The multiple outflow boundaries and surface boundaries left behind by prior convection can act as initiation mechanisms for subsequent storms, even in the absence of strong synoptic forcing. In short, the question of whether later windows are more or less dangerous than Thursday is genuinely open, and it does not default to less dangerous. The conveyor belt metaphor is useful but incomplete. A factory conveyor belt produces identical items. This atmospheric conveyor belt is producing systems that interact with each other's outputs, and that interaction is the element of the 12-day pattern that is hardest to model and hardest to communicate. We will return to this in the section on the latent heat feedback loop, where the interaction between storms and their parent system becomes explicit. But the immediate question is why the conveyor belt is running at this pace in the first place, and the answer involves physics at a scale that operates far above the weather we experience at the surface. Part 7. Rossby wave stall mechanics. The jet stream does not flow smoothly around the planet like water in a garden hose. It meanders, it amplifies, it buckles into large-scale waves called Rossby waves, which are the fundamental wave structures of the atmosphere and ocean at planetary scale. These waves form as a result of the variation in the Coriolis effect with latitude, the change in the Earth's rotation influence as you move from equator to pole. When Rossby waves are small in amplitude, the jet stream flows relatively zonally, which means in a roughly west to east direction, and weather patterns cycle through quickly because the waves propagate eastward at a reasonable speed. When Rossby waves amplify, the jet stream buckles into large north-south excursions, and the speed at which those waves move eastward slows dramatically. A sufficiently amplified Rossby wave can stall. A stalled Rossby wave is the root cause of what is happening over North America right now. The key is not just that a trough has formed over the western United States, but that the trough is not moving. This is the pattern lock condition at its physical foundation. The deep trough sitting over the western United States is the low-pressure part of a Rossby wave that has amplified to the point where its normal eastward propagation has been disrupted. Wave energy that would normally continue propagating downstream into the Atlantic has instead broken, which is the meteorological term for a Rossby wave that has reached its nonlinear limit and effectively scattered its energy, rather than continuing to propagate coherently. What wave breaking does to the downstream pattern is to create a blocking situation. The ridge that exists downstream of the Western Trough, which sits over the eastern United States, is being reinforced by the energy convergence from the breaking wave. A reinforced ridge is a stubborn ridge. It resists the eastward propagation of the weather systems trying to move through it. The cyclones generated by the Western Trough track northeastward and run into this ridge, which deflects them toward Canada or redirects their energy, and the fundamental configuration of trough west and ridge east persists. New short waves from the Pacific encounter the same trough, are amplified by the same dynamics, generate new cyclones, and the cycle repeats. The timescale for this kind of pattern persistence can range from a few days to a few weeks. The model signal through 12 days is suggesting the former rather than the latter, but the honest answer is that the exact duration of the pattern lock is one of the more uncertain elements in this forecast. What the models agree on is that the configuration is not going to break down before at least the first two severe weather windows have played out. Weather window 3 in early May is still operating under this locked pattern, or is already transitioning to something else is where the forecast confidence genuinely decreases. Here is why this matters for the central question of this entire story. The Rossby wave stall is what ensures the conveyor belt keeps running. It is what guarantees that after Thursday's system, there will be another severe weather opportunity in a few days, and potentially another one after that. But understanding that the wave is stalled tells you nothing about whether any individual system within the pattern produces one catastrophic tornado or 100 forgettable ones. The large-scale dynamics ensure the pattern. They do not determine the local outcome. The gap between those two levels of knowledge is where all the meaningful uncertainty lives, and it is a gap that the next piece of the puzzle, the tropical and extratropical interaction driving this configuration, illuminates further. Part 8. MJO and PNA. Alignment, the hidden driver. There is a signal in the tropical Pacific that does not produce tornadoes, does not create blizzards, and cannot be seen on any radar display, but its fingerprints are on every weather event that is about to unfold across the United States. The Madden-Julian oscillation is a pulse of enhanced and suppressed convection that travels eastward around the equator over the course of roughly 30 to 60 days. It is not a storm. It is an organized perturbation in the tropical atmosphere, a broad wave of cloudiness and rainfall that moves slowly eastward, completing roughly one full circuit of the tropics over the course of 4 to 8 weeks. Forecasters track its phase carefully because its location at any given time influences the behavior of the jet stream over the mid-latitudes in ways that are well documented, even if the exact physical pathways are still being refined by researchers. The current MJO phase is one that historically favours the development of a persistent western trough over North America. The tropical convection in this phase is positioned in a location that injects wave energy into the mid-latitudes in a pattern that reinforces and extends the blocking configuration we already discussed. This is not a direct causal link like a billiard ball hitting another billiard ball. It is a probabilistic reinforcement. The MJO does not dictate what the jet stream does. It shifts the odds in favour of certain configurations, and right now it is shifting those odds toward exactly the configuration that is already in place. Layered on top of the MJO signal is the Pacific North American pattern, known to forecasters as the PNA. The PNA is a large-scale wave pattern that describes the relationship between ridges and troughs across the Pacific and North American sectors. When the PNA is in its positive phase, it tends to favour a ridge over the eastern Pacific and western North America, and a trough over the central and eastern continent, which is close to but not exactly the current configuration. When the PNA is in its negative phase, the opposite tends to prevail. The current PNA configuration is one that forecasters have identified as supportive of the locked trough pattern, and combined with the MJO alignment, it produces a probabilistic estimate for pattern persistence in the range of 60 to 70% through at least the next 10 days. That number, 60 to 70%, is worth understanding clearly. It does not mean there is a 60 to 70% chance of severe weather on each day of the next 10. It means there is a 60 to 70% chance that the large-scale pattern remains configured in a way that continues to support severe weather opportunities. The individual storm probabilities are much more dependent on the mesoscale factors that the MJO and PNA cannot predict. But the persistence likelihood tells you that the conveyor belt is more likely to keep running than not, and that the three-window forecast structure is more likely to verify than to fall apart due to a pattern change. The interaction between tropical and extratropical forcing is a relatively modern area of forecasting. The science has developed substantially over the last 20 years, and its incorporation into operational extended range prediction is one of the reasons that 12-day forecasts today carry more useful information than they did a decade ago. It does not make them precise. It makes them directionally reliable, which is a different and more honest kind of skill. There is a speculative angle worth acknowledging here. When multiple teleconnection signals, meaning large-scale remote forcing patterns like the MJO and PNA, are simultaneously aligned in a configuration that favours a particular weather regime, the persistence of that regime may be enhanced beyond what either signal would suggest individually. Some researchers have called this teleconnection stacking, the idea that reinforcing large-scale signals can create pattern locks that are more durable and more extreme than any single forcing mechanism would produce. This is not established forecast doctrine. It is an active area of research. But it is relevant to understanding why this 12-day window is attracting the attention of the extended range forecasting community. What the MJO and PNA alignment guarantees is the structural persistence of the pattern. What it does not and cannot determine is how the energy within that pattern is released on any given day at any given location. That release is governed by mesoscale processes, by the behaviour of individual boundaries and caps and dry lines, by the microscale interactions between convection and its environment, and ultimately by an element of non-linear unpredictability that the atmosphere reserves for itself. The alignment ensures the stage is set. The performance remains unwritten. Part 9. The latent heat feedback loop. There is a conversation happening between the storms and their parent system that most weather coverage ignores. When a thunderstorm develops, it does not passively consume the atmospheric energy available to it. It actively modifies the environment around it. The most physically significant modification is the release of latent heat. As water vapor condenses into cloud droplets and liquid water freezes into ice crystals, the phase transitions release the energy that was originally required to evaporate the water in the first place. This energy does not disappear. It is deposited directly into the mid-levels of the atmosphere, warming the air column at altitudes of roughly 15 to 30,000 feet. This seemingly local process has consequences that reach far beyond the individual storm. Warming at mid-levels in the atmosphere reduces the air pressure at the surface beneath and around the storm because warmer air is less dense and exerts less weight per unit area. If you have a large cluster of thunderstorms or an extensive area of convection releasing latent heat simultaneously, the collective mid-level warming is enough to measurably deepen the surface low associated with the frontal system. The cyclone does not just drive the storms drive the cyclone. This is the diabatic deepening process, and it is not a negligible secondary effect. It is one of the primary mechanisms by which rapidly intensifying cyclones can deepen faster than the purely dynamic components of the jet stream and trough would predict. For the 12-day pattern, this feedback loop operates at a scale that transcends any individual storm day. As each successive shortwave crosses the Rockies and generates a new cyclone, the convection that fires along the warm sector of that cyclone releases latent heat into the mid-levels. That heat warms the air aloft, strengthening the downstream ridge and simultaneously deepening the upstream trough. A stronger downstream ridge is a more effective block against the eastward propagation of the trough, which extends the pattern lock. A deeper upstream trough is a more energetic source region for the next shortwave. The result is a system that is, in a thermodynamic sense, partially fueling itself through its own convective output. This is not a perpetual motion machine. The energy ultimately traces back to the sun's heating of tropical and subtropical ocean surfaces, which drives the evaporation that loads moisture into the atmosphere in the first place. But the feedback loop means that the 12-day pattern is not simply running on a fixed energy budget that depletes monotonically through time. It is interacting with its own outputs in ways that can sustain or even amplify the activity beyond what the initial large-scale forcing alone would produce. The moisture transport from the Gulf of Mexico is the critical link in this chain. As long as the large-scale wind pattern continues to direct southerly flow across the Gulf and into the central United States, fresh moisture is continuously available to fuel the next cycle of convection. Each storm taps the moisture, converts it to precipitation, releases the latent heat, and then the evaporation from saturated soils and recovering vegetation partially recharges the low-level moisture content for the next event. The moisture pool does not fully recover between events, but it does not fully deplete either. It operates in a kind of dynamic equilibrium that keeps the thermodynamic forcing available for successive systems. The question worth raising carefully is whether this feedback mechanism could extend the pattern duration beyond what the large-scale forcing alone would predict. The Rossby wave stall determines the structural persistence of the trough ridge configuration. The MJO and PNA alignment modify the probability of that persistence. But the latent heat feedback from the convection itself may be providing an additional reinforcement mechanism that prolongs the locked state. If this is the case, then the 3-window forecast might be conservative. There could be a 4th window. There could be a 5th. This is speculative. The models do not currently show a 5th distinct severe weather window, and beyond roughly 12 days, the forecast uncertainty is large enough that specific storm development cannot be meaningfully predicted. But the physical mechanisms that could support an extended active period are present and operating, and the possibility that the atmosphere is reinforcing its own pattern through convective feedback should not be dismissed as an idle theoretical curiosity. It may matter for what happens beyond the 12-day window this video is focused on. What matters most for understanding the central thread of this story is this. The latent heat feedback confirms that the 12-day pattern is not a passive sequence of independently triggered storms. It is an active, partially self-reinforcing cycle in which the storms and the system are in conversation with each other. And yet, for all of that conversation, for all of that feedback and amplification, the fundamental question of whether any individual event in the sequence produces concentrated catastrophe or dispersed lesser impacts remains as open as ever. The macro-scale physics are working overtime to ensure the pattern persists. The micro-scale physics retain full authority over what each event delivers. Part 10. The 12-day compression hypothesis. Consider a different way of thinking about time in meteorology. A typical late April through early May period, considered in historical terms, might produce 1 or 2 significant severe weather outbreaks, separated by quiet intervals of several days to a week. There might be 3 or 4 days with at least marginal severe weather potential across the Central Plains, spread across a 20 to 25-day window. The active days are interspersed with quiet days, and the total accumulated severe weather activity, measured in confirmed tornado reports, significant wind events, and large hail documentation, is distributed across a month in a way that allows for recovery between events, both in the physical sense of atmospheric recharging and in the practical sense of emergency response and community recovery. What the current 12-day pattern appears to be doing is compressing that activity into a dramatically shortened window. 3 severe weather windows in 12 days, with the possibility of a 4th if the pattern extends, represents a clustering of convective events that is unusual even within the climatological context of April and May, which are the historically most active months for severe weather across the central United States. The European Centre for Medium-Range Weather Forecasts model, which is widely regarded as the most reliable extended-range guidance available, is showing the locked trough configuration maintaining through at least the period ending in early May. Multiple ensemble members, which are the individual model runs that account for uncertainty by starting from slightly different initial conditions, are showing severe weather-favourable configurations on multiple days across this period. The concept of temporal clustering, the bunching of extreme events into a compressed window rather than their spread across a longer period, is something that researchers studying climate variability and extreme event statistics have been examining with increasing interest. When individual events occur in rapid succession without intervening quiet periods, the cumulative risk is not simply additive. Infrastructure that was damaged by the first event is more vulnerable to the second. Emergency resources that were committed to the first response are less available for the second. Communities that have not yet received warning follow-up or damage assessment from the first event are poorly positioned to prepare for the next. The psychological and organisational fatigue associated with repeated events in rapid succession is real and measurable. The rarity of extended slight risk day sequences, the formal designation that the Storm Prediction Centre applies to days with a broadly elevated severe weather threat, is worth noting. Multiple consecutive slight risk days are not uncommon in active spring periods, but multiple slight risk days interspersed with enhanced risk and moderate risk designations across a 12-day window would represent an unusually active and sustained period. The forecast products currently being generated by the SPC reflect elevated concern about this sequence, not just individual events. The climate context here requires careful framing. There is active scientific discussion about whether the frequency of certain kinds of extreme weather events is changing, and specifically about whether temporal clustering of severe weather outbreaks is increasing. The evidence is mixed, and the detection of trend signals against the natural variability of severe weather is statistically challenging. This video will not claim that the current 12-day pattern is attributable to any specific long-term trend, because the attribution science does not support that kind of specific event attribution with confidence. What can be said honestly is that the physical mechanisms supporting this kind of event, specifically the tendency for Rossby wave amplification and blocking configurations, are subjects of ongoing research regarding whether their frequency and persistence are changing. The current event is a data point, not a conclusion. What the 12-day compression hypothesis ultimately suggests is that the question of whether this pattern produces one defining catastrophic event or a series of moderate events has a temporal dimension as well as a geographic one. Even if no individual event in the 12-day window reaches the threshold of historic significance, the combined effect of multiple events in rapid succession may produce aggregate outcomes in terms of damage, disruption, fatigue, and resource depletion that rival or exceed what a single major outbreak would generate. This is a different kind of significance, less dramatic, less photogenic, but no less real in its consequences. The pattern is loaded, the compression is real, and what happens next in that central Kansas to North Texas corridor on Thursday night is the first test of how this 12-day story begins to resolve. Where exactly do the storms fire? How do they develop? And which mode does the atmosphere choose? Those answers come in windows. Part 11. Window 1, April 23rd. Through 24, the test case. Thursday is where the story gets personal. The initiation sequence on April 23rd will not play out uniformly across the entire high-risk area simultaneously. The early afternoon hours will likely see storm development in the northern tier, specifically across South Dakota and Nebraska, where the combination of surface heating and approaching dynamics will be sufficient to overcome the convective inhibition earlier in the day when the cap is thinner. These initial storms are important not primarily for their own tornado potential, but for what they do to the environment downstream. Northern initiation storms can produce cold pools that spread south, altering the moisture and stability pattern across Kansas and Oklahoma during the hours when those areas need their own environment to remain intact for the evening peak. This is one of the most legitimate sources of uncertainty in the Thursday forecast. If the early South Dakota and Nebraska storms are vigorous enough and extensive enough, their cold pool outflow could fundamentally alter the surface thermodynamic profile across central Kansas by late afternoon, dampening the instability precisely where and when the models are projecting STP values near 10. This is a mesoscale interaction that regional and national models struggle to predict accurately because it depends on storm behavior that cannot be fully specified in advance. Some model runs show the early storms remaining relatively innocuous, producing modest cold pools that do not significantly contaminate the southern environment. Other runs show them becoming more organized, with outflow boundaries that push southward and reshape the dry line position in Kansas. The evening focus shifts to Oklahoma, and specifically to the triangle connecting the Oklahoma City metropolitan area to the north, the Wichita Falls area to the southwest, and the Tulsa region to the east. This is where the highest STP values are projected to align with the peak shear window, and it is the zone that the Storm Prediction Center and regional National Weather Service offices will be watching most intently. Storm initiation in this zone, if it occurs in the discrete mode, produces the scenario where the central question of this entire story has its most extreme potential answer. A single supercell tracking northeast from central Oklahoma through the evening hours, maintaining mesocyclone integrity in a 130-knot jet stream environment with STP at 10, is the realization of the worst-case scenario that the atmospheric setup is theoretically capable of producing. But the clustering tendency is always present in environments like this, and it creates a genuine dilemma for storm chasers and meteorologists alike. Do you position for the discrete supercell scenario in the triple point zone and risk being near the most violent possible tornado? Or do you position for the linear system scenario that is statistically more likely, and that requires a very different geographic strategy? This is not a recreational question. It is a life safety question for anyone in the risk zone, because the two scenarios require different preparedness responses. Discrete supercell tornadoes are more likely to be tracked individually by radar and receive specific tornado warnings with relatively accurate paths. Linear system tornadoes, which are often embedded within squall lines and may form with very short lead time, are harder to warn precisely and harder to shelter from in manufactured housing or vehicles. The nighttime timing deserves a separate and honest moment of attention. If peak storm development truly arrives in the 9 to 10 p.m. window, the public preparedness situation is fundamentally different from a late afternoon event. Children are in bed. Adults who are monitoring weather apps at 6 p.m. have gone to sleep by 10. The social amplification of warning messages through community networks is slower and less reliable at night. The NWS offices covering this region are well aware of this and will be communicating proactively, but the effectiveness of warnings depends not just on issuance, but on receipt and action, and nighttime receipt and action rates are measurably lower than daytime rates. Does the system pass the test on Thursday? That framing is important because Thursday is not just an event, it is the first data point in a 12-day experiment. How the atmosphere handles its energy on Thursday, whether it concentrates into a few violent structures or disperses across a broad area, will provide information that helps calibrate the forecasting community's expectations for windows 2 and 3. The atmosphere does not learn from its own behaviour, but meteorologists do. Thursday's verification, whatever it produces, will refine the uncertainty envelope for what comes next. Part 12. Storm Mode Wars. There is a battle that happens inside every major severe weather outbreak before a single radar signature appears, and it is fought entirely between atmospheric processes that are invisible to the naked eye. On one side of this battle is the ingredient set that favours discrete supercells. Strong directional wind shear in the lowest kilometre of the atmosphere encourages the formation of tight mesocyclones in isolated storm structures. High Cape values concentrated in a narrow thermodynamic corridor support tall, vigorous updrafts that can maintain their rotation. Low lifted condensation level heights, which in this setup are projected to be in the 300 to 500 metre range over the Oklahoma region, bring the condensation level and associated cloud base close to the surface, reducing the distance a tornado must extend to reach the ground. A sharp, well-defined dry line provides a focused initiation mechanism that limits the number of initial storm cores to a manageable few. All of these factors are on the side of discrete supercell development. On the other side of the battle is the physics of cold pools. Every thunderstorm, as it produces precipitation, also generates a downdraft. That downdraft spreads out along the surface when it reaches the ground, creating a boundary of cold, stabilized air called a cold pool or outflow boundary. Cold pools are not inherently bad. Supercells can maintain themselves in the presence of modest cold pool activity because their strong rotation allows them to continuously import fresh, unstable inflow from the environment ahead of the cold pool. But when cold pool activity becomes aggressive, when the downdraft is particularly vigorous, or the storm motion is slow enough that the cold pool expands rapidly, it can undercut the inflow that the storm needs to maintain its rotation. When multiple storms are generating cold pools simultaneously, those cold pools can merge and create a broad area of stabilized surface air that effectively ends the discrete phase and forces a transition to a linear squall line structure. The transition from supercell to squall line is not a gradual process. It can happen over the course of 20 to 40 minutes, and when it does, the character of the severe weather threat changes fundamentally. A squall line produces tornadoes, but they are typically shorter-lived, weaker, and harder to anticipate than supercell tornadoes. They are produced by different mechanisms, usually mesovortices embedded along the leading edge of the line, and they give less visual and radar warning than the classic hook echo signature of a supercell tornado. A squall line also produces widespread long-duration wind damage from its bow segments, which can be devastating to large areas, but typically does not produce the concentrated catastrophic destruction of a violent long-track supercell tornado. The atmosphere effectively has a choice, and it makes that choice based on processes that operate at scales too small to be fully resolved by the operational models available to forecasters. The specific humidity profile of the boundary layer at a point in central Oklahoma at 5 p.m. on Thursday, the exact position of a cold pool boundary from a convective cluster in Nebraska 6 hours earlier, the precise orientation of the dry line when the first storm core fires, and whether that storm core can maintain its isolation long enough to establish a dominant mesocyclone before its neighbours develop their own cold pools. This is why identical-looking model forecasts of the large-scale parameters can produce radically different storm outcomes. The model sees STP at 10. The model sees the favourable wind shear profile. The model projects storm initiation along the dry line. What the model cannot resolve is the microscale competition between those storm cores, and the outcome of that competition determines everything about whether Thursday is remembered as the day one violent tornado tracked across 3 counties, or as the day severe weather produced widespread damage across a broad region without a single event that stands out from the noise. Meteorologists have a phrase for this kind of forecast situation: high-end potential with mode uncertainty. It acknowledges simultaneously that the ceiling of what this environment can produce is extreme, and that the probability of actually reaching that ceiling depends on factors that honest forecasting cannot resolve. The Storm Prediction Center issues moderate and high-risk outlooks for these setups, and the language of those outlooks consistently includes conditional statements precisely because the storm mode question does not have a deterministic answer before the atmosphere reveals it in real time. What is the most likely outcome? If historical analog behavior in similar setups is any guide, the probability distribution leans toward a mixed mode event. Some discrete supercells in the early period of the evening in the Oklahoma and Kansas zone, followed by upscale growth into a more linear structure as the cold pool interaction takes hold through the overnight. In that scenario, the tornado risk is real but distributed, and the wind damage risk is high and widespread. The tail risk, the scenario where one supercell maintains discrete structure through the peak environment window, is present and cannot be forecasted away. It is real. It is just less probable than the mixed mode scenario. Part 13, Window 2, April 25th through 28. The reload. Before the discussion of Thursday's window has even had time to settle, the next system is already crossing the Pacific. The second shortwave in the train is a few days behind the first, and as the first cyclone tracks into Canada and its severe weather window closes, the second shortwave is approaching the Rockies and beginning its own Lee cyclogenesis process. By Friday, the front associated with window 1 will have cleared most of the southern plains, and the cool, drier air behind it will begin the process of being undercut by the next surge of Gulf moisture streaming north on the backside of the retreating first cyclone and then on the leading edge of the developing second system. By Saturday, the thermodynamic recovery is already underway. By Sunday, the models are showing a setup that, in terms of instability and shear, is beginning to approach Thursday's parameters. The reload is one of the more alarming aspects of the pattern lock for the forecasting community. In a normal severe weather season, a major outbreak is typically followed by 3 to 5 days of recovery time. The air mass that entered with the cold front is cool, dry and stable. The boundary layer needs time to recover its moisture and instability. The upper level pattern needs time to cycle back to a configuration that supports another major system. Under the current pattern lock, that recovery time is dramatically compressed. The cold air intrusion behind window 1 is relatively shallow and short-lived because the pattern is already driving another warm surge northward. The Gulf moisture return is forecast to be rapid and substantial, with surface dew points recovering to near Thursday levels by Sunday or Monday. The April 27th and 28th window is the current focus of the reload attention, with Sunday showing the strongest signal across most of the model guidance examined by operational forecasters. The setup for this second window has some differences from Thursday that are worth noting. The storm track of the second cyclone is projected to be somewhat further east than the first, which shifts the highest risk zone from Kansas-Oklahoma toward the Missouri-Arkansas-Tennessee corridor. This is a different kind of geography for severe weather. The terrain is more complex, the population density in some areas is higher, and the agricultural communities that anchor this region have a different infrastructure profile than the open plains. One of the more interesting aspects of the second window is the concept of a preconditioned atmosphere. The soils across the risk zone will already be saturated from the first system's rainfall. The surface energy budget will be altered because a wet surface evaporates differently than a dry one, maintaining higher near-surface humidity and potentially boosting instability recovery. More subtly, the surface boundaries left behind by the first system's convection, outflow boundaries, differential surface moisture patterns, regions of anomalous soil temperature, all become part of the mesoscale environment that the second system's storms will interact with. These boundaries can act as additional initiation triggers or as shear enhancement zones that elevate the tornado potential in locations that the synoptic scale models would not otherwise flag as highest risk. This is the cumulative environment effect in action, and it is one of the reasons that the second window cannot simply be evaluated as an independent event with a fresh atmospheric slate. It is inheriting conditions from window 1, some of which enhance the severe weather potential and some of which complicate the forecast. The multi-scale interaction of inherited boundaries, altered soil conditions, and a reloaded thermodynamic profile makes the April 27th through 28th window, in some respects, a more complex forecast challenge than Thursday. The raw ingredients may be slightly less extreme, but the mesoscale complexity is higher. There is also the question of escalation. Later events in a pattern lock, particularly when the latent heat feedback mechanism is operating, can sometimes produce a more amplified atmospheric response than earlier events because the downstream ridge has had more time to strengthen and the upstream trough has had more time to deepen. This is not guaranteed. Model guidance does not currently show an obviously larger signal for window 2 than window 1, but the possibility that the second window outperforms the first should not be dismissed purely on the basis that it comes later. The atmosphere is not necessarily winding down, it may be winding up. Part 14, Dixie Alley awakens. Something has been missing from the 2026 Southeast tornado record. By late April of a typical year, the region that meteorologists informally called Dixie Alley, the corridor spanning parts of Louisiana, Mississippi, Alabama, Tennessee, and Arkansas, that experiences a separate and somewhat distinct severe weather season from the traditional plains tornado season, would normally have several significant events in the books. The geography of this region makes it particularly susceptible to certain types of tornado-producing systems, especially during the cool season and early spring when Gulf moisture is already plentiful but upper-level dynamics are still strong. This year through mid-April, the southeast has been anomalously quiet. The setup has not come together in this region the way a climatological year would predict. The April 28th setup changes that. As the second shortwave system moves into its mature phase, the warm sector extends eastward into the Mississippi Valley and beyond. the combination of moisture returned from the Gulf, afternoon instability, and the approach of the mid-level dynamics associated with the second cyclone creates a window during which the southeast enters the severe weather risk zone for the first time this season in a meaningful way. The particulars of this setup carry the same uncertainty that characterises the entire 12-day period, but with the additional complexity that the southeast region has some geographic and cultural characteristics that alter the risk profile. Forest cover is more extensive, which can impair visual detection of approaching tornadoes and complicate damage surveys. Manufactured housing is prevalent in rural areas across the region, which consistently correlates with elevated fatality rates in tornado events. And critically, this particular episode is forecast to arrive during the overnight hours on April 28th into 29th, when the nighttime risk amplification we discussed for Thursday applies with equal force. The central question connects directly back to where this story began. Even as the Dixie Alley window opens, even as a new region enters the risk zone, the fundamental uncertainty about whether the energy concentrates into a few destructive events or disperses across many lesser ones remains exactly as unresolved as it was on Thursday morning. New geography, same unanswered question. Part 15, Window 3, May 3rd through 6th, Low confidence, high consequence. Beyond roughly 7 days, weather forecasting enters a zone where the honest answer to many specific questions is, we don't know yet. The signal showing a potential third severe weather window in the May 3rd through 6th period is present in the European Model Extended Range Guidance and in a majority of the Global Ensemble Forecast System members. What that means practically is that more model runs are showing a pattern favourable for severe weather in that window than are showing a quiescent pattern. That is a signal worth communicating, but it must be accompanied by an honest calibration of what the confidence is at that range. The specific track of the third cyclone, its central pressure, its storm mode, its exact timing, the location of the dry line, the STP values in the highest risk zones, none of those details have meaningful forecast skill at 10 to 12 days. What the models are showing is a structural continuation of the locked pattern, not a specific event forecast. Why does a low confidence signal at extended range deserve inclusion in this story? Because if it verifies, the cumulative context by that point will be unlike anything in the recent memory of severe weather responders across the central United States. By May 3rd, if Windows 1 and 2 have produced significant severe weather events, emergency managers will have been operating in sustained high alert mode for 10 days. The National Weather Service offices covering the Central Plains will have been running extended operations and briefing cycles for over a week. Volunteer fire departments, search and rescue teams, and public health organisations will have committed resources to prior events. Media organisations will have sustained severe weather coverage for an extended period. And the public, depending on how Windows 1 and 2 are verified, will either be in a state of heightened vigilance or, more dangerously, beginning to experience warning fatigue. Warning fatigue is a documented behavioural phenomenon in meteorological risk communication research. When severe weather warnings are issued frequently over an extended period, particularly if earlier warnings resulted in events that were less severe than the worst-case scenarios that motivated protective action, the subsequent compliance rate with warnings decreases. People habituate to the alarm. They begin to discount the probability that this warning, unlike the last few, will materialize into something genuinely dangerous. This is a rational cognitive process in one sense, as the human brain is wired to update its threat assessment based on recent experience. But it is maladaptive in the specific context of a third window arriving after 2 prior windows because the third window's atmospheric physics is completely indifferent to the preceding social history. The atmosphere does not know it has already alarmed people twice. The possibility of an escalating pattern where each successive shortwave arrives into an increasingly preconditioned environment adds another dimension of concern to the third window. If the latent heat feedback has been operating actively for 10 days, if the downstream ridge has been reinforced by multiple cycles of deep convective heating, and if the upstream trough has deepened through the same process, the third system in the sequence might be the most dynamically intense of the 3. That is speculative. The models do not currently support it as the most likely scenario. But the physical mechanisms that would enable it are active, and acknowledging the possibility is more honest than dismissing it. The pattern may outlast the forecasts. That is, in the end, the most important thing to understand about Window 3. It exists at the edge of reliable prediction, it is real as a structural possibility, and its verification or non-verification will be shaped by processes that will not become clear for several more days. The atmosphere is writing this story in real time, and no model output available today can tell you how it ends. Part 16. 1 tornado versus 100 storms. The same atmospheric energy can write two completely different stories, and the alphabet it uses to choose between them is too small to read at forecast range. This is the essential paradox of the 12-day pattern. The energy is real, the dynamics are real, the STP of 10 is real, the conveyor belt of Pacific shortwaves is real, the pattern lock is real. And yet none of that reality resolves the question of whether this sequence of events produces a single tornado that will be studied in atmospheric science courses for a generation or a season. Average sequence of events that is notable only in retrospect for its compressed timeline. The history of severe weather meteorology contains examples of both outcomes from similar setups, and the examples are instructive precisely because they involve near-identical environmental parameters, producing radically different results. There are outbreak days in the historical record where a STP environment as strong or stronger than Thursday's was realized, where discrete supercells fired in the favorable zone, where long-track violent tornadoes occurred, and where the damage paths are still visible in aerial imagery decades later. There are also outbreak days in the historical record where STP values were similarly extreme, where storms fired but immediately began interacting destructively with each other's cold pools, where the storm mode transitioned rapidly to linear, and where the event produced widespread wind damage and brief weak tornadoes, but nothing that qualified as the violent defining event the setup theoretically supported. What distinguishes these outcomes is not the large-scale environment. It is the storm spacing, the cold pool interaction, the specific position of individual initiation points relative to each other, and ultimately a chain of cause and effect events that begins at scales too small for deterministic forecasting to resolve. The first storm that fires sets the conditions for the second. The second storm's cold pool interaction with the first determines whether a third storm that fires between them sees a favourable or an unfavourable environment. These are domino processes, and the first domino's exact position and velocity are not fully known. There is something almost philosophically uncomfortable about this. We have built extraordinary scientific infrastructure around severe weather prediction. Doppler radar networks that detect rotation in storms in real time, numerical weather prediction models running at sub-kilometre grid spacing, ensemble forecast systems that sample uncertainty across thousands of model runs, dedicated atmospheric research aircraft that fly into severe weather environments to gather in situ data. The National Weather Service has 13,000 employees. The Storm Prediction Center issues outlooks, watches, and mesoscale discussions with a sophistication that did not exist 30 years ago. And all of that infrastructure, all of that knowledge, all of that accumulated scientific achievement still cannot tell you whether Thursday produces one catastrophic tornado or 100 forgettable storms. This is not a failure of science. This is the nature of nonlinear chaotic systems. The atmosphere is a fluid system operating at Reynolds numbers so astronomically high that deterministic prediction of small-scale features is fundamentally limited by the propagation of initial condition errors through the system. The errors are small at first, but they double in a characteristic time, and after enough doublings, the specific local details of storm behavior are effectively unpredictable. This is the Lorentz butterfly effect, not as a metaphor but as a literal physical property of the atmospheric system that we inhabit. The energy distribution problem, whether the atmosphere concentrates its energy into a few violent events or disperses it across many lesser ones, is ultimately a question about whether the nonlinear dynamics of convective storms favour a focused or a distributed energy release. And the answer to that question, at forecast ranges beyond a day or two, genuinely depends on initial condition details that no observational network can specify perfectly. We know the large-scale story. We cannot know the sentence-level details. This uncertainty is the reason that the forecasting community, when confronted with extreme setups, communicates in probabilities rather than certainties, in conditional language rather than declarative statements. The experienced meteorologist who looks at Thursday's setup and says, "This could be catastrophic, but I cannot promise you it will be," is not being evasive. They are being honest in a way that respects both the science and the public they serve. Part 17. The cap problem, the invisible gatekeeper. Between the energy that the atmosphere has loaded and the storms that would release it, stands a feature that has no visual presence on a radar display and cannot be seen from the surface, and that feature may ultimately determine Thursday's outcome more than any other single variable. The convective cap, formerly called the convective inhibition, or CIN in meteorological notation, is a layer of relatively warm air that sits above the boundary layer and prevents the buoyant surface air below it from rising freely into the upper troposphere. Think of it as a temperature inversion, a region where air temperature increases with height rather than decreasing, which removes the buoyancy that would otherwise allow surface air parcels to ascend and form thunderstorms. The cap is not unusual. It is present on most days across the central United States during spring and early summer. What makes it important is its thickness and its specific temperature anomaly, because those properties determine how much surface heating is required to erode it sufficiently to allow storm initiation. A moderate cap in a favourable severe weather environment is actually a desirable ingredient for the tornado enthusiast setup, because a moderate cap prevents premature storm development while allowing the instability to continue building through the afternoon hours. When the cap finally breaks in the late afternoon, the storms that fire emerge into an environment that has been building energy all day, and they fire from a focused initiation mechanism such as the dry line rather than from everywhere simultaneously. This is the discrete supercell scenario's best-case path to realization. The complication arises at both extremes. A cap that is too weak breaks early, allowing storms to fire across a broad area throughout the afternoon and evening. This produces the overcooking scenario where dozens of storm cores compete for the available instability. Cold pools merge, and the environment transitions to a linear mode before the peak shear window is ever reached. The discrete supercell scenario is defeated by its own abundance. A cap that is too strong stays intact through the evening peak window, suppressing all convection until after the instability window has passed, or until the forcing dynamics weaken after midnight. Storms that fire into a weakening shear environment can still produce tornadoes, but they are less likely to sustain the long mesocyclone life cycle that produces the most violent and longest track events. The Thursday setup has a forecast cap strength that sits in the middle range, strong enough to potentially hold through much of the afternoon, but weak enough that the late afternoon heating combined with the approaching dynamic, forcing from the jet and the trough should erode it near or after sunset across the Oklahoma and Kansas triple point zone. The uncertainty in this estimate is not small. The cap's exact strength depends on the precise temperature and moisture profile of the atmosphere at altitudes of roughly 3,000 to 6,000 feet, and the model guidance shows meaningful differences in that profile from run to run. There is also the dry line mixing variability complication. During the afternoon hours, the intense surface heating over the elevated dry terrain west of the dry line generates a deep, well-mixed boundary layer that erodes moisture and stability in the dry sector. The eastward mixing of this dry air across the dry line can, under certain conditions, erode the cap in the warm sector near the dry line before the dynamic forcing arrives. If this happens, storms fire in the early evening before peak shear is reached, and they do so in a marginally weaker shear environment than would exist 2 to 3 hours later. These early storms may or may not maintain discrete structure through the peak window. It depends on their individual cold pool behaviour and their relationship to the cap in their immediate vicinity. 1 to 2 hours. That is the timing window within which the cap's behaviour will determine the storm mode that dominates Thursday evening. 1 to 2 hours earlier than the current central forecast for dryline initiation, and storms fire into suboptimal shear. 1 to 2 hours later, and storms fire into post-peak shear as the dynamics begin to weaken. The optimal window is narrow, and its exact timing is uncertain. The difference between the three scenarios, early, optimal, or late initiation timing, cannot currently be forecasted with deterministic skill at 1 to 2 day range. This is the invisible gatekeeper, not dramatic, not visible on radar, not discussed in most weather coverage, but controlling the outcome as completely as any of the dramatic large-scale features that have filled this entire discussion. The cap problem is where the 12 days of atmospheric setup, the pattern lock, the conveyor belt, the STP of 10, the triple point, the jet streak, all of that complexity and energy and potential passes through a bottleneck so narrow that a change of 2 degrees Fahrenheit in an inversion layer at 8,000 feet could redirect history. Part 18. Fire, Flood, Snow, the Overlooked Impacts. It would be easy, given the tornado narrative that dominates this entire story, to treat fire, flood, and snow as supporting characters who do not get meaningful screen time. But the fire weather threat across the southern high plains is not a minor subplot. Red flag conditions across the Texas and Oklahoma panhandles, combined with vegetation that dried out rapidly after a relatively wet winter, represent a fire spread potential that can outpace any ground-based suppression effort. The fires that have swept through the southern high plains in recent decades have destroyed thousands of structures, eliminated livestock across enormous ranges, and in some cases moved fast enough to trap vehicles on rural roads. The downslope winds that feed this threat on Thursday will be operating independently of any storm development. They do not need tornadoes to do their damage. The flooding across the upper Midwest will compound for days after Thursday, as the heavy rainfall from the warm sector interacts with a drainage system already at capacity. The rivers that flood do not care about whether a tornado occurred in Oklahoma. They are responding to their own cumulative loading, and their behaviour will affect communities across multiple states for days to a week after the storm system passes. And the blizzard conditions in the Dakotas will strand livestock, disrupt transportation, and create hypothermia risks in communities where the cold sector of this system delivers a genuine late-season winter impact. These hazards are the mechanism by which the atmosphere's energy gets released even in the failure scenario for tornadoes. If the cap holds, if storms cluster, if the STP-10 environment never gets properly tapped, the fire, flood, and snow do not care. They are on their own timetables, driven by their own atmospheric mechanisms, and they will proceed regardless of what the dry line does on Thursday evening. This is the 5-hazard fingerprint of a system built like January arriving in April, and every one of those 5 hazards is real. Part 19. Conspiracies, Signals, and Energy Reality. Every time an unusual or extreme weather event approaches, a particular kind of claim emerges alongside the legitimate forecasting discussion. It arrives on social media within hours of the first model runs, spreads through comment sections under meteorological updates, and circulates in parallel with the actual science being done by atmospheric researchers. The claim takes several recognizable forms, but its underlying shape is always the same: that what we're about to experience is not weather but engineering, weather modification, chemtrails seeding storm systems, ionospheric heaters manipulating the jet stream, government programs engineering extreme weather for undisclosed purposes, directed energy weapons steering hurricanes, cloud seeding operations scaled up beyond any publicly acknowledged capacity. These claims are not new, and the reason they keep reappearing is partly psychological and partly physical. The atmospheric dynamics that produce events like Thursday's cyclone are genuinely complex, involving the interaction of dozens of variables across multiple spatial and temporal scales. The coincidence of multiple extreme factors aligning simultaneously looks, from a human pattern recognition perspective, as if someone planned it. The atmosphere's behaviour seems too perfectly configured to be random, too precisely timed to be accidental, too catastrophically effective to be the result of mere physics doing what physics does. Human cognition did not evolve to reason about systems at this scale. We evolved to detect intention in the behaviour of other agents, to recognise the signature of planning in the arrangement of objects, to identify causation in sequences of events. When we see a storm arrive exactly when forecasters predicted, intensify exactly where the model suggested, and produce damage in patterns that correlate with the terrain, the agent detection machinery in our minds reaches for the most readily available explanation. Someone did this. Someone meant for this to happen. The alternative, that a planet-scale fluid dynamical system produced a coherent structure through the unguided interaction of pressure gradients and rotational forces, does not feel intuitively satisfying even when it is demonstrably correct. The energy comparison is where the physics of these claims collapses. The total kinetic energy in a single major extratropical cyclone is on the order of 10 to the 20th power joules, which is roughly equivalent to several thousand nuclear weapons detonating simultaneously and continuously over multiple days. Let that figure settle for a moment. Not one nuclear weapon, not the entire Cold War arsenal released in a single instant. several thousand weapons detonating continuously for days on end. That is the energetic reality of one storm of the kind we are tracking. The entire global output of human energy generation, every power plant on Earth operating simultaneously, every coal plant and nuclear reactor and hydroelectric dam and wind farm and solar array combined, amounts to a small fraction of the energy in one such storm. Humanity, as a whole civilization, does not generate enough power in a year to equal what a mid-latitude cyclone dissipates in a day. There is no technology available, no program funded, no device constructed that could generate, steer or modify a storm system at this scale. The energy gap between human capability and atmospheric power is not 10 times or 100 times, it is many orders of magnitude. To put this in concrete terms, if you took every aircraft on Earth and flew them continuously in coordinated patterns, every ionospheric heater ever built and ran them at peak output, every cloud seeding operation ever funded and scaled them up by factors of thousands, the combined input would still be thermodynamically invisible against the backdrop of what the atmosphere is doing on its own. You would be trying to redirect a river by breathing on it. You would be attempting to turn a freight train by pushing on it with a feather. The comparison is not rhetorical, it is quantitative, and the numbers are not close. This is why the serious atmospheric science community, including researchers who have spent entire careers studying deliberate weather modification, treats claims of large-scale engineered weather with the same seriousness that physicists treat perpetual motion machines. Cloud seeding, the actual documented practice, can under optimal conditions marginally increase precipitation from clouds that were already primed to produce it. It cannot create storms, it cannot steer them, it cannot intensify a cyclone or weaken a hurricane or redirect a jet stream. The entire industry of operational weather modification, accumulated over decades of research and deployment, has produced interventions that are statistically detectable only through careful study of long-term precipitation records. Nothing in that body of work suggests a hidden capability waiting to be unveiled. The physics forbids it. The patterns that feel engineered are the result of the Rossby wave physics, the MJO alignment, the PNA configuration, and the Lie cyclogenesis mechanisms that we have spent this entire video discussing. They feel intentional because they are coherent, because they follow physical laws that produce recognizable structure, because the atmosphere has its own kind of order even when that order manifests as catastrophic weather. Coherence is not evidence of design. A snowflake is coherent. A galaxy is coherent. A hurricane's spiral bands are coherent. These structures emerge because the equations governing their formation admit only certain kinds of solutions, and those solutions often look organized to eyes accustomed to seeing organization as the fingerprint of intention. The atmosphere is a pattern-generating machine. It produces patterns whether or not anyone is watching, whether or not anyone wants them to appear, whether or not their appearance aligns with any human agenda. When a cyclone's track aligns with population centers, when the timing of a storm coincides with a politically sensitive moment, when the geographic distribution of damage seems to follow some legible logic, the explanation is not that someone arranged these correlations. The explanation is that we live on a planet whose weather systems interact with a geography we have already shaped, a civilization we have already built, a calendar we have already filled with meaning. The storm does not know about our elections or our infrastructure or our historical anniversaries. It is doing what pressure gradients and temperature differentials and rotational dynamics require it to do. We are the ones bringing the narrative. The uncertainty that is central to this story, the genuine impossibility of determining whether Thursday produces 1 tornado or 100 storms, is not the uncertainty of a controlled experiment with a hidden variable. It is the fundamental irreducible uncertainty of a chaotic physical system operating at scales that exceed our prediction capabilities. Chaos, in the mathematical sense, does not mean randomness. It means that systems governed by deterministic laws can nonetheless produce outcomes that are in principle unpredictable beyond certain time horizons, because arbitrarily small differences in initial conditions amplify into arbitrarily large differences in outcomes. This is the actual reason forecasters cannot tell you exactly what Thursday will bring, not because they are hiding something, not because the true cause is being concealed, because the mathematics of the system itself guarantees that prediction becomes probabilistic past a certain horizon, and no amount of better sensors or faster computers will ever fully overcome this limit. It is baked into the equations, And this is in some ways the harder truth to sit with. The engineered weather narrative offers, beneath its conspiratorial surface, a strange kind of comfort. If someone is doing this to us, then someone could stop. If there is a hidden controller, there is at least a controller, which is psychologically preferable to the alternative. The alternative is that we live inside a planetary-scale physical system that occasionally produces outcomes capable of killing thousands of people for reasons that are completely indifferent to our existence, predictable only probabilistically, and beyond any human capacity to prevent or redirect. The storm is not punishing anyone. The storm is not sending a message. The storm is a consequence of atmospheric physics operating on a rotating planet heated unevenly by a distant star, and its arrival at our doorstep is neither personal nor planned, natural, not engineered. That distinction matters not because engineered weather would be worse, though in some philosophical sense it might be, but because the response to natural catastrophic weather and engineered catastrophic weather are entirely different. One requires us to prepare, adapt, build resilient infrastructure, improve forecasting, and accept that some uncertainty is irreducible. The other sends us chasing phantoms while the actual storm keeps coming. The cyclone does not care which response we choose. It will arrive on Thursday regardless. What we choose determines only whether we meet it ready or distracted, and readiness has never been served by looking for villains in a sky that has no author. Part 20. The ending the atmosphere hasn't chosen. Return with me to the number we started with, 986 millibars, a late April cyclone that should not have the central pressure of a January system, a storm that exists at the intersection of seasonal thermodynamic abundance and winter-like dynamic forcing. An event that has assembled 5 distinct hazard processes across a continental footprint, loaded the atmosphere with STP values that belong in the historical record books, triggered a pattern lock that will keep generating severe weather windows for 12 days, and still, despite all of that, has not yet decided what kind of story it is writing. The entire 12-day pattern exists in a kind of superposition. 2 outcomes simultaneously present in the probability distribution. On one side of the distribution sits the concentrated disaster scenario. One supercell fires in the triple point zone in central Kansas or northern Oklahoma at 9 p.m. on Thursday evening. It maintains discrete structure because the cap held through the late afternoon and eroded just as the peak shear window arrived. The mesocyclone tightens as the storm moves northeast through the optimal shear environment. A tornado touches down in a rural county, and then it does not lift. It stays on the ground, intensifying as the supercell ingests increasingly unstable Gulf air, and it tracks northeast through the night across county after county, widening, strengthening, becoming the kind of event that rewrites the meteorological record books. And while that one tornado is happening, Window 2 is already loading, and Window 3 is assembling itself at the edge of the forecast models. The 12-day compression hypothesis verifies, and the 2026 severe weather season is defined by its opening 2 weeks, in a way that will inform the research literature for years. On the other side of the distribution sits the dispersal scenario. Elevated convection from Nebraska fires early on Thursday afternoon, sending cold pool outflow southeast into Kansas by early evening. The outflow boundary encounters the dry line and shifts it eastward by 50 miles into a region where cap strength is slightly higher and where the surface moisture is modestly reduced. Dry line initiation occurs at 8 p.m. but over eastern Kansas and Oklahoma, and the initial storm cells immediately begin competing. 3 supercells within 50 miles of each other are generating cold pools that interact destructively before any of them can establish dominant mesocyclone structure. By 9 p.m., the storm complex is merging into a bow echo structure. Significant wind damage occurs from Kansas to Missouri through the overnight hours. Multiple weak tornadoes are confirmed. No single event tracks more than 5 miles. The aggregate damage report is real but unspectacular, and Window 2 produces a similar dispersal outcome, and Window 3 never fully verifies because the pattern lock weakens earlier than the extended model suggested. Both of those outcomes are inside the probability distribution that exists right now. Neither is the forecast. Both are real, and this is where the deepest truth about weather prediction lives. We have built our entire scientific apparatus around the goal of reducing uncertainty, of collapsing probability distributions into single-point forecasts, of answering the question, what will happen, with confidence and precision. And we have made extraordinary progress. The lead time for hurricane track forecasts has tripled in 50 years. The warning time for tornadoes has increased from near zero in the 1950s to an average of 13 minutes today. Quantitative precipitation forecasts have improved dramatically with each generation of numerical models. The science is genuinely, measurably advancing. And yet here we stand, 48 hours before one of the most dynamically extreme late April setups in the modern record, and the most fundamental question, concentrated catastrophe or dispersed lesser events, genuinely cannot be answered. Not because of a failure of science, not because of insufficient data, not because the models are malfunctioning, because the physics of the question, the non-linear, scale-dependent, chaotic physics, places this specific detail outside the reach of deterministic prediction at this range. The first domino is still in the forecaster's hand. They know the shape of the table, they know the mass of the dominoes. They cannot know exactly where the chain goes after that first one falls. The 12-day window is real, the pattern lock is real, the STP of 10 is real, the 5 simultaneous hazard processes are real, the conveyor belt is real, the latent heat feedback is real, the Rossby wave stall is real, the MJO alignment is real. All of it is real, and all of it is telling you that the atmosphere has assembled something extraordinary over the central United States. What it has not told you, what it cannot yet tell you, is whether extraordinary energy becomes extraordinary history, or whether it disperses into the noise of a season that goes on to produce other, quieter days without ever quite detonating the load it carried in this window. There is something in that uncertainty that is, if you sit with it long enough, more interesting than the certainty would be. The atmosphere is not withholding the answer to be cruel. It genuinely has not chosen yet. The specific arrangement of molecules in the boundary layer over central Oklahoma at 8:47 p.m. on Thursday evening has not yet occurred. It is still in the future, still unwritten, still in a state that quantum mechanics would describe as a superposition of possibilities, and that meteorology describes as a probability distribution. The cat is still alive and dead. The tornado is still present and absent. The season-defining catastrophe is still both certain and impossible. And when Thursday night arrives and the atmosphere finally, irreversibly makes its choice, the choice will have been made by a pressure gradient at 986 millibars, by a jet streak at 130 knots, by a cap that either held or broke at exactly the wrong or right moment, by a cold pool boundary from Nebraska that travelled 50 miles in exactly the wrong or right direction, by the specific dew point value at a single surface observation station that either supported or suppressed the initiation of the single supercell that either became the story or did not. The pattern is certain. The story it writes is not. But here is the thing that keeps the atmospheric scientists and the storm chasers and the forecasters awake at night, not with dread, but with the particular kind of alertness that comes from watching something enormous and irreducible approach. The next 12 days are not a single story. They are a series of decisions the atmosphere is about to make, one after another, each one shaped by the ones that preceded it, each one carrying the possibility of concentrated disaster or dispersed consequence, each one carrying the STP fingerprint of an environment that is objectively, measurably, historically primed for violence. Window 1, Window 2, Window 3, each one a new question. Each one with the same answer waiting somewhere in the chaotic arithmetic of a fluid system that has been running its calculations since before humans had words for what it produces. We have words for it now. We have numbers for it. 986 millibars, STP 10, 130 knots, 48 to 72 hour recurrence, 3 windows, 12 days. We have everything except the most important thing, the ending. And the atmosphere, indifferent to our forecasting frameworks, our ensemble members, our mesoscale convective discussions, and our probability estimates, is writing that ending right now, one parcel of air at a time, in a language that operates below the resolution of every tool we have built to read it. The pattern is certain. The story it writes is not. And somewhere in that gap between the certainty of the environment and the uncertainty of the outcome, between the 986 millibar cyclone that should not exist in April and the tornado that may or may not ever touch down, between the scientific precision of the STP index and the chaotic irreducibility of the convective trigger, Somewhere in all of that lives the actual, honest, unvarnished answer to why we watch the sky. Not because we know what it will do, because we do not.